Hello, in this presentation, we will review chemistry that you have learned in your general chemistry class before taking anatomy and physiology. There are three parts that we will discuss. In part one, we will look at the structure of atoms. In part two, we'll look at the formation of ions. And in part three, we will examine types of chemical bonding that occurs between atoms. For further information, you can read Chapter 2 in your textbook, and study questions 3 and 4 pertain to this information. So there are 92 naturally occurring elements that make up all matter. They are displayed in the periodic table and arranged according to their properties. In this course, you will not need to memorize the periodic table, but we will use it as a tool. The elements that are most abundant in the human body include oxygen, carbon, hydrogen, and nitrogen. The four of them make up 96.1% of your body mass. Also important are some lesser elements found in smaller quantities, about 4% of your body mass, including calcium, phosphorus, potassium, sulfur, sodium, chlorine, iodine, and iron. You should know the chemical symbols for all of these, the major elements and the lesser elements. And most of them are straightforward, but I will point out two that are particularly important and are not straightforward. Potassium, for example, the symbol is K, and sodium, the symbol is Na. These symbols refer to the Latin terms for each of the elements. For example, the Latin name for sodium is natrium. We focus on chemistry in the human body because all of the physiological processes that we will study are dependent on the interactions between atoms and molecules that consist of these main elements. There's a field in chemistry called biochemistry that focuses on the behavior and properties of the common elements found in living organisms, and you may wish to take a further course in biochemistry before you enter your healthcare program. Before we discuss chemistry in any detail, we should review some definitions. There are four terms that you should be familiar with: element, atom, isotope, and ion. An element is a fundamental type of substance that composes matter. An atom is the smallest particle that keeps all the properties of that element. An isotope is a form of an atom. It will have a different atomic mass than other atoms, but still be part of the same element. These alternate forms of an atom that are the same type of element have a different number of neutrons. We will discuss those in more detail. An ion is a form of an atom that has a charge. The charge exists because the atom has an unequal number of protons and electrons. So let's review the structure of a single neutral atom, an atom without a charge. There are three subatomic particles: protons, neutrons, and electrons. In the nucleus, there are protons and electrons, and then the electrons orbit the nucleus. They float around the nucleus a certain distance away. So the nucleus is central, and these different levels where electrons are located are called orbitals. The first orbital can hold 2 electrons. The next orbital can hold 8, and the rest can also hold 8. The outermost orbital that contains at least one electron is called the valence orbital. It's this valence orbital that will dictate the chemical behavior of the atom. Here's another generalized model of an atom, a neutral atom. In this diagram, we see that there are 10 electrons, 2 in the first orbital, 8 in the valence orbital. That's a total of 10. Therefore, we know that there are also 10 protons because all atoms are electrically neutral. An electron is negatively charged, whereas a proton is positively charged. The periodic table, of course, arranges atoms or elements according to the number of protons. We also call this the atomic number. So if we look at the entry for just oxygen, we see that oxygen has an atomic number of 8. That means it has 8 protons. We can extrapolate, therefore, and say that a neutral oxygen atom also has 8 electrons. The atomic mass is another property that's listed in the periodic table for each element. The entry for oxygen lists the atomic mass at 16. The atomic mass is really the mass of the nucleus. It equals the mass of all the protons plus the mass of all the neutrons. Because a proton and a neutron weigh the same, each designated as having one atomic mass unit, we can use this atomic mass and the atomic number to determine how many neutrons exist in one neutral atom of oxygen. So, for example, oxygen's atomic number is 8. That tells us there are 8 protons. The atomic mass is listed at 16. That tells us that there are 16 protons and neutrons. So if you take 8 away from 16, you get 8. So there are 8 protons and 8 neutrons in one atom of oxygen. Let's use the periodic table to make sure that you can do this on your own. And I've chosen carbon because oxygen and carbon are the most common or abundant elements in the human body. First, what number is the atomic number and which is the atomic mass? From those two numbers, can you predict how many protons there are, how many neutrons, and how many electrons in one carbon atom? The answers are on the next slide, so if you wish to pause before you turn to the next slide, please do so. The atomic number for carbon is 6, and the atomic mass is 12. So that tells us there are 6 protons, 6 neutrons, and because there are 6 protons, there must be 6 electrons. I referred to isotopes previously. For a given element, such as carbon, there are different forms of atoms that weigh differently. These different forms vary in terms of the number of neutrons. Therefore, they vary in the atomic mass. So the different forms are called isotopes. There are 3 different isotopes of carbon that I've shown here at the bottom. Carbon-12 weighs 12, carbon-13 weighs 13, and carbon-14 weighs 14. They all 3 have an atomic number of 6. So that means they all have 6 protons. They all have 6 electrons to balance the positive and negative charges. What varies is the number of neutrons. So carbon-12 will have 6 neutrons. 6 protons plus 6 neutrons equals 12. Carbon-13 will have 7 neutrons because 6 protons plus 7 neutrons equals an atomic mass of 13. Carbon-14 will have 6 protons and 8 neutrons because 6 plus 8 is 14. The reason isotopes are important to us, we'll see later, is because how they're used in medical procedures. But the atomic mass listed in the periodic table, you'll often notice, has decimal places, 12.011 for carbon. That atomic mass is calculated by taking into account the frequency of the different types of carbon atoms that exist in nature and their frequency in nature. The isotopes will have the same chemical behavior because they have the same number of protons and the same number of electrons, but they will vary in their physical properties, such as how fast they may decay, and this is due to their difference in mass. There are also radioisotopes and hydrogen isotopes that are used in medical technology. MRI and contrast dyes use hydrogen isotopes. PET scans use a variety of different radioisotopes, and iodine 123, for example, is used to detect thyroid cancer. I can't explain how exactly, but it's a certain isotope of iodine. For hydrogen isotopes, there are 3. Hydrogen 1 weighs 1, deuterium has an atomic mass of 2, tritium has an atomic mass of 3, and that's because they vary in the number of neutrons, shown here as gray spheres. We often draw atoms as a Lewis dot structure. It's a helpful tool because it's really the electrons that will dictate, the valence electrons that will dictate how an atom will interact with another atom. So a Lewis dot structure only draws the valence electrons around the chemical symbol. Since the atomic number of carbon is 6, there are 6 electrons. If we were to draw all the electrons, we would see that there are 2 in the first orbital and 4 in the second orbital. But to simplify that drawing, we just draw the valence orbital electrons around the chemical symbol. So that's a Lewis dot structure. The reason that the Lewis dot structure is helpful is that it tells us at a glance how many electrons are missing in this valence orbital. And that's based on something known as the octet rule. So atoms tend to establish fully complete valence orbitals. So in the case of hydrogen, since it only has 1 electron, it's only got that first orbital. It can only fit 2, but it wants to fit 2. Carbon has 6 electrons total, but 4 in its valence. That tells us right away it can accept 4 more in that valence orbital. To meet the octet rule, an atom might share, gain, or lose electrons. And it does so by interacting with neighboring atoms. So for each atom drawn below, see if you can predict whether the atom would lose or gain electrons. How many would it have to lose or gain to fulfill the octet rule, or to fulfill the octet rule? The answer's on the next slide, so if you wish to pause, please do so. Since carbon has 4 electrons, it could either gain 4 or lose 4. It does tend to gain, so it gains 4 electrons. Oxygen has 6 electrons in its valence shell. It could lose 6 or gain 2, but it would be a lot more energy efficient just by gaining 2. Hydrogen can gain or lose 1, and it does either in different circumstances, we will see most often that it loses this electron and becomes positively charged. Nitrogen has 5 valence electrons, and therefore it tends to gain 3 electrons to fill its valence orbital. Okay, let's talk about how ions are formed. This is part 2. Ions are forms of atoms that have unequal numbers of protons and electrons. So they're either positively or negatively charged. A positively charged atom is called a cation. It has more protons than it does electrons. An anion is a negatively charged atom. It has more electrons than protons. Now, the process by which an atom becomes either a cation or an anion has a term. So oxidation is one and reduction is another term. So an atom that becomes oxidized, it has lost an electron, forming a cation. If instead an atom is reduced, it has gained an electron to form a negatively charged anion. Sometimes it's hard to remember if oxidation results in a cation or an anion, or if reduction forms a cation or an anion. The way I remember it is that a cat is positive. Kitty cats are positive, so now I know an anion's negative. The other thing relating to oxidation and reduction is there are 2 different kind of monikers or acronyms you can use. I learned Leo goes grrr. So if you lose an electron, you're oxidized. If you gain an electron, you're reduced. Other students have told me that they learned oil rig, which you decipher as oxidized. Oxidation is loss. Reduction is gain of an electron. This picture shows how a cation or an anion is formed. So it's showing us oxidation and reduction. In the first example of oxidation, we have a sodium atom. Sodium has 11 electrons. We know that because it has 11 protons. So there are 2 electrons in the first orbital. There are 8 in the next orbital. That leaves 1 electron. This last electron is in the valence orbital, and that's very unstable. It would have to gain 8 to fill the octet rule. What it tends to do instead is lose the 1 electron. When it loses that electron, now it only has 10 electrons. So this resulting atom, which is really an ion, has 11 positive charges in the nucleus, but only 10 negative charges surrounding it. So that's a net positive charge. We call that a cation, and oxidation has occurred. This picture on the right shows reduction, or the formation of an anion. In this case, we use a chlorine atom that has 17 electrons. We know it has 17 electrons because there are 17 protons. The first orbital has 2 electrons. The second orbital has 8 electrons. That's 10. So there's 7 left over. So there are 7 electrons in the outermost orbital. To fill the octet rule, it needs to gain 1. So it gains an extra electron. When it does so, it now has 18 electrons, but still only 17 protons. That means more negative charge than positive charge, and an anion has formed. Hydrogen ions are interesting because they are often referred to as a proton, and to avoid confusion in the future, I wanted to explain why hydrogen ions are called protons. It's because a hydrogen atom doesn't have any neutrons. So when that atom ionizes, it loses its only electron, and the only thing that's left is a proton. So I'm going to review that a little bit. Here is a neutral hydrogen atom. What exists in a neutral hydrogen atom, which has an atomic number of 1 and an atomic mass of 1, is 1 proton in the nucleus. Since there's 1 proton, it has 1 electron. Balanced charge, neutral. No neutrons. If this hydrogen atom ionizes and becomes an ion, a hydrogen ion, it loses this electron. It has lost a negative charge, so it's going to be positively charged due to the proton in its nucleus. And that's all it has, is a proton. So this hydrogen ion is often referred to as just a single proton. Some other highly reactive compounds that we might encounter, or you've heard of anyway, we won't really discuss them very much, are called free radicals. Free radicals are either atoms or compounds that have an unpaired electron. That makes it very reactive. Electrons like to be paired. They're at least, one partner. Of course, a compound or an atom also likes to have the valence orbital filled. But what happens is these free radicals can donate that electron, that unpaired electron, to another compound, or it can take away an electron from another compound. This isn't uncommon, and in fact is a normal metabolic function that happens in all of our cells. But sometimes in high quantities, these free radicals can interact with molecules that they shouldn't and cause cellular damage that the body doesn't have a chance to repair quick enough. Some examples of harmful free radicals are superoxide anion, hydrogen peroxide, and hydroxyl radical. So hydrogen peroxide, we probably use to destroy bacterial cells when cleaning a wound. This is a picture of a hydroxyl radical that's showing you an unpaired electron. The body can deal with any free radicals that normally occur through our metabolic reactions. First, it can convert them into less harmful compounds. The liver cells do that. Also, there are lots of repair mechanisms in various cells throughout the body that repair damage done by these free radicals. Our body also produces natural antioxidants called enzyme antioxidants that neutralize free radicals. And then finally, our diet consists of antioxidants, including vitamins A, C, and E. So normally free radical numbers are kept in check. Okay, part 3 of the general chemistry review involves chemical bonding between atoms. And we'll talk about 2 different types of chemical bonding: ionic bonding and covalent bonding. Ionic bonding occurs when oppositely charged ions are attracted to one another to form ionic compounds. This often involves a metal and a non-metal being attracted to one another. Covalent bonding occurs when electrons are shared by 2 atoms. This forms a physical connection and covalent compounds. Let's first look at ionic bonding a little bit. First, ionization has to happen. So sodium and chlorine, which we've already looked at, turn into ions. This usually happens in an aqueous solution, water solution. But the resulting positively charged sodium is attracted to the negatively charged chlorine. That's an ionic bond. the positive charge and the negative charge being attracted to one another. When ionic compounds form, they usually result in crystal-like structures because a negative or anion is really a cloud of negativity three-dimensionally and is attracted to multiple cations around all of its sides. So it forms a crystal-like structure that we refer to as salts. Some salts that are commonly found in our body include calcium phosphates, calcium carbonate, potassium chloride, and some other ionic compounds in our bodies are referred to as electrolytes. So these electrolytes are capable of conducting an electrical current in water because they dissociate. They're present in our blood, urine, cytoplasm of our cells in many different locations. And one that's particularly important in this list is sodium bicarbonate, because sodium bicarbonate ionizes to form this bicarbonate ion, which can bind to a hydrogen ion, and that helps regulate pH of our blood. We will talk more about pH balance in anatomy and physiology too, and you do not have to memorize all of these electrolytes. You should just be aware of the fact that they are ionic compounds that ionize in water and can conduct an electrical current. They are important because when they're not at the appropriate levels or they're imbalanced, they can cause problems. They have different effects that range from muscle cramps to brittle bones, even affect the nervous system causing coma or maybe the heart causing cardiac arrest. They're important because they participate in metabolic reactions. For example, sodium, calcium are very important for nerve and muscle function. And then they also affect water balance in our body. We call that osmotic balance, making sure that there is appropriate amounts of water inside cells as well as outside of cells. And as I mentioned, they're essential for nerve and muscle tissue function. The last type of bonding is called covalent bonding, and in this situation, atoms share electrons. Ions are not formed. There is no gain or loss of an electron by an atom, so no oxidation or reduction occurs. It tends to happen between like atoms. For example, two nonmetal atoms may form a covalent bond, or two metal atoms will form a covalent bond. The goal is always to fill the valence orbital. This picture shows a covalent bond between two hydrogen atoms, and when it's a single covalent bond, there are two electrons involved. This atom has donated one electron. This atom has donated the other. The two electrons make up the bond. And because this atom now has two circling around its nucleus, its valence shell or orbital is complete or full. This one, the same is true. Because they're sharing, they have filled that outermost orbital. Other types of covalent bonds include double covalent bonds and triple covalent bonds, but the same principles apply. In the second picture or middle picture here, we see two oxygen atoms forming a double covalent bond. That has happened because of the number of electrons required by each atom to fill their valence orbital. Oxygen has 6 electrons in its valence orbital. 1, 2, 3, 4, 5, and then 6. It's donating 2 of those to this oxygen, who also had 6. The 2 donated, I should say shared, make this oxygen's valence orbital full. It now has 8, and so does this oxygen. Nitrogen, because it has 5 valence electrons, needs 3 more, so it shares 3, and this nitrogen shares 3, so we get a triple covalent bond. Usually when we write covalent compounds, we use a molecular formula, as you see on the right here. Carbon dioxide, for example, we usually write CO2. Ammonia, we usually write NH3. Water is common, H2O. But that doesn't tell us anything about what atoms are bonded to which atoms. So sometimes we'll use a structural formula. You can come up with a structural formula by first drawing the Lewis dot structures for each atom, for the carbon and for an oxygen, and figuring out how many electrons each atom needs to fill the orbital. So carbon dioxide, we see carbon is in the middle, and it is sharing 2 electrons with this oxygen and 2 electrons with this oxygen. Ammonia also has nitrogen in the middle. It is sharing 3 electrons with 3 different hydrogen atoms. And water has a very specific structure with this kind of an angle between its 3 atoms that we'll look at in a lot more detail later. So thank you, and I hope you found this helpful.